come over is Griffiths 2.1.4, continuous charge distributions. So in the past example, we talked about a set of charges that were generating an electric field, and we wanted to evaluate the electric field at some point P. And we did that by saying that, all right, my electric field can be found at some point in space by taking the sum of all of those electric fields being generated by all of those source charges. All right, we found this distance, found this distance, found this distance, found this distance, and you add up all of those individual electric fields, and you found the total electric field. However, it's not always the case that the things that are generating your fields, your source charges, they're not always discrete elements on a surface where you can define their position. Right? They might be some continuous distribution, right? And that's what we're going to talk about today. So there are analogous versions of charges for every type of dimension that we want to talk about. Okay, so I have discrete charges. I have line charges. I have surface charges, and I have volume charges. All right. And I said charges, but really what each of these are densities. This is a line charge density. This is a surface charge density. And this is a volume charge density. So if I have some little bit of charge, I can define that little bit of charge by saying, all right, well, that's just my line charge density multiplied by some little bit of a line, or my surface charge density multiplied by some little bit of an area, or my volume charge density multiplied by some little bit of a volume. Now notice I've kept the prime coordinates on here because the prime coordinates are specifically related to the charges that are generating fields. Okay, so now if I want to go ahead and figure out what the electric field is from, say, a line charge with line charge density lambda, I can just integrate that. That's 1 over 4 pi epsilon naught. The integral of my charge density located at some position r prime over r squared, still in the r hat direction, and multiplied by dl prime. So my integral is going to be over my prime coordinates, or the locations where my charges are at. All right. That's for the line. There's analogous versions for the surface and the volume. All right, so given that, let's go ahead and do example 2.2 together. 2.2 looks a lot like the previous problem we did together, but instead of having discrete points, we have a line of charge density lambda. Okay. Let's see, the definition of the problem says that I have a segment of straight line with length 2L, means that this goes from, that's L, all right, that's L. I believe the coordinates here are X and Z again. And I want to know what the point, the electric field is at some point P, that is a distance Z above my plane. Okay, so last time we just added the contributions from two charges, and we remembered that, the electric field component from the right in the X direction canceled the electric field component of the left charge going in the X direction. And we're left with just some net electric field in the Z direction because of the symmetry. Right? That's the same thing that's going to happen here. So let's pick, instead of picking a particular point that was a charge to start from, let's pick a particular area that has a charge density. Okay, so let's pick this region of my straight line that has a charge density on it. I will go ahead and call that my DL prime. And in the end, I'm going to figure out what the electric field contribution is from this to point P. And I'm going to integrate over all of my possible choices of DL prime. Okay, so this is my script R vector, meaning that this vector right here in red, since it points from the origin to DL prime, or to my patch, that is R prime. And this vector that points from my origin up to point P is vector R. Okay. So let's go ahead and construct what vector R is. That is 0 in the x-hat direction, z in the z-hat direction. My vector R prime, that's equal to, I guess I haven't said how far away we are. We're going to say we're going to go x in the x-hat direction and 0 in the z-hat direction. Now, this is where Griffiths, I don't like what Griffiths has done. If you look at footnote 3, it says, ordinarily I'll put a prime on the source coordinates, but there's no confusion here, so I will erase it for simplicity. All right. Well, this is the only example 2.2. We haven't done very many examples, so I'm going to keep the primes, okay, because the primes are associated with where we are for our charges. And I'd hope you do the same. Okay, so that means that if I have R and R prime, I can calculate what my script R vector is. That becomes R minus R prime, right? Because it points from the source to the field. Which means that I have minus X prime in the X hat direction plus Z in the Z hat direction. Okay, the magnitude of my vector is X prime squared plus Z squared, square root. And while I'm at it, I'll just define that the hat, the unit vector, is minus X prime X hat plus Z, Z prime over X prime squared plus Z squared. All right, so let's go ahead and fill all that in to figure out what my integral is. So I know that my electric field at my point in space that I care about is going to be 1 over 4 pi epsilon naught, and integrate, right? Can integrate over my charge density. Here my charge density is a constant, so it no longer depends on my position R prime, so that makes it a little easier. I'm going to integrate over DL prime, and I need R hat, which is minus X prime X hat plus Z hat over X prime squared plus Z squared to the 1/2 times 1 over magnitude R squared. All right, that's just this, and I'm left with the 3/2 here. All right, I've simplified something that I waited to do till the last step last time, but I'll do it right away here. Okay, so this is 2 integrals, right? Because I'm integrating over where my charges are, and I need to do an integral for the X hat and the Z hat direction. Now, we still haven't figured out what DL prime is. DL prime is the infinitesimal length that changes as you go along your charged region. Well, for us, DL prime, since we've oriented our charged object along the X direction, is just dx prime. Okay, so that's something that we can change here. I'll change it manually by erasing. That's dx prime. Okay, so now I need to put limits on my integral, dx prime. What does x prime begin at and end at? Well, it's going to start from the left and end on the right, right? Minus L to L. Okay, so I'm going to break this up into two integrals and then make an argument that I'm not going to do one of them. My lambda is constant. That's lambda over 4 pi epsilon naught. Two integrals, 0, oops, not 0, negative L to L of minus x prime dx prime x hat over x prime squared plus z squared 3/2 plus a new integral from negative L to L of z hat dx prime over x prime squared plus z squared to the 3/2. Now, since this is two integrals, one is over the x direction and one is over the z direction, and we made an argument that the x direction should be 0, all of that information is contained in this integral. Whatever the result of that integral is going to be the electric field, the total electric field in the x direction. So if you were to take that integral and calculate it, you should get 0. Right? I would recommend that you do that to prove that that's true to you, but that will give you 0. And I'm left with one integral I'm actually going to solve. Now, we're going to be doing a lot of integrals together, like a ton of integrals. So I would recommend that you find your favorite integral solver. I use Wolfram Alpha to do this for me symbolically. And I would plug in probably the indefinite integral and put the bounds in manually. So I do that, make sure I'm integrating over my dx prime, so that's this variable in the bottom, and I'm left with 1 over 4 pi epsilon naught. I get a 2 lambda L over z times z squared plus L squared. All right. So I don't have a direction. That's not good. Z hat direction. Okay, so here's the electric field from my line charge, which is a length of 2L and has some charge density lambda. Okay, so what? Like, we have this functional form, but how do I even know if it's reasonable or not? Right? We're going to be testing our solutions with things that we know the answer to. So we're basically going to be taking limits of our solutions in different directions to see if we believe that answer or not. Okay, so what happens in a physical limit where I go all the way down, where I change my point P so it's at the origin, right? I just said that I'm looking for the electric field at some point Z away from my axis. Right, but what if I set Z down to 0, right? So now I have this region of space that has charge density lambda. I go ahead and take my electric field at some point in space, 1 over 4 pi epsilon naught, 2 lambda L over Z squared plus L squared in the Z hat direction. Okay. What happens if I set Z to 0 here? I think it's pretty complicated, right? So physically, I would expect that all of the electric fields will be pointed in the right direction, from the left side, and all of the electric fields from the right side will be pointed in the left direction, and everything will cancel out. But I see that if I put a 0 here, I get 0 on the bottom of my expression, and that will blow up to infinity. So something has to be done differently. All right, we'll talk about this a little bit more in the class, but what we're going to have to do is take the appropriate limit, right? Take the limit where z goes to 0 in the right fashion, right? Usually using the binomial expansion. Okay, so that's not the limit that we can test right now, but we can test another limit that's much easier. All right, let's imagine I zoom very far away. My point in space is so high that my little rod of charge looks tiny. Okay, this is the regime where z is much bigger than L. Okay, so if z is much bigger than L, my electric field 1 over 4 pi epsilon naught 2 lambda L over z squared plus L squared. This term right here, z squared plus L squared, right? That's basically just z squared, since L is so small. Square root of z squared is z times z is z squared. I'm left with 1 over 4 pi epsilon naught 2 lambda L over z squared. Forgot the z hat again. So what does this look like? This looks like a point charge, right? I have my 1 over 4 pi epsilon naught. I have my distance away from my point charge, and I have my direction. And the only difference is this numerator up top. So it looks like a point charge. Let's see, the source from the field from a point charge, where that point charge has charge 2 lambda L. Okay, so we're going to be taking a lot of limits as we move. As we find our solutions, we're going to take a lot of limits so that we can test our solution instead of just blindly accepting whatever math pops out in the end.